On the far side of the solar system in November of 2018, an instrument on a spacecraft that had already been flying for 41 years recorded something that, according to decades of careful peer-reviewed modeling, wasn't supposed to line up the way it did. It wasn't a single strange reading. It was a pattern, confirmed independently, that directly contradicted a basic prediction about how the boundary of our solar system should behave. And NASA's own scientists, describing it afterward, didn't pretend to have a tidy explanation ready. One of the mission's longtime physicists said, plainly, on the record, "We don't understand why that is." That spacecraft is Voyager 2, and the data it sent back from the true edge of our solar system remains, even now in 2026, only partially explained. This is the story of what Voyager 2 actually found out there, why it directly contradicted what scientists expected, and why some of it still doesn't have a confirmed answer. To understand why this particular data mattered so much, you first have to understand where Voyager 2 was when it recorded it, and how it came to be there at all, because the story of how it got to that boundary is itself a big part of why its data turned out to be so valuable. Voyager 2 launched on August 20th, 1977 from Kennedy Space Center in Florida, 16 days before its twin, Voyager 1, lifted off from the same launch pad. Both spacecraft were built for a 5-year mission with a fairly modest goal on paper: fly past Jupiter and Saturn, take photographs, gather measurements, then fade quietly into retirement. Nobody involved in building either spacecraft seriously expected either one to still be transmitting data back to Earth nearly 50 years later. Despite the numbering, Voyager 1 was placed on a faster, more direct trajectory and eventually overtook its sibling, reaching Jupiter and Saturn first before using a close pass by Saturn's moon Titan to angle sharply out of the plane of the planets entirely, trading away any further flybys for a closer look at Titan's thick atmosphere. Voyager 2 took a slower, more patient route. And because of a rare alignment of the outer planets that occurs only once every 175 years or so, mission planners realized they could send it onward past Saturn to Uranus and Neptune as well, an opportunity that wouldn't come around again for well over a century. Voyager 2 remains to this day the only spacecraft in history to visit all 4 giant planets up close, discovering new moons and rings at nearly every stop along the way, including the only close-up images humanity has ever captured of Uranus and Neptune. That longer, more elaborate journey through the planets meant Voyager 2 reached the true edge of the solar system considerably later than its twin. Voyager 1 crossed the heliopause, the boundary where the sun's outward stream of charged particles finally loses its strength against the pressure of the material filling the space between stars, in August of 2012. Voyager 2 didn't reach that same boundary until November 5th, 2018, 6 years later, on the opposite side of the solar system entirely. But Voyager 2 had something its twin no longer had by that point: a fully functioning plasma science experiment, the instrument specifically built to directly measure the speed, density, and temperature of the solar wind surrounding the spacecraft. Voyager 1's version of that same instrument had failed back in 1980, shortly after its Saturn flyby, decades before it ever reached the boundary, meaning its 2012 crossing had to be confirmed indirectly, through secondary signals like a sudden jump in cosmic ray density. Voyager 2's crossing was different. Its instrument recorded the solar wind speed around the spacecraft dropping sharply and then reading essentially 0, watched directly, in real time as it happened, rather than pieced together after the fact. "This is what we've all been waiting for," said Suzanne Dodd, Voyager's project manager at NASA's Jet Propulsion Laboratory, in NASA's official announcement of the crossing. "Now we're looking forward to what we'll be able to learn from having both probes outside the heliopause." What they learned turned out to directly challenge some of the basic assumptions scientists had built their models around for decades, and it came in several distinct pieces, each one worth understanding on its own. The first surprise involved distance, and it's the kind of finding that only becomes strange once you understand what scientists expected beforehand. Researchers had long predicted that the heliopause's distance from the Sun should shift depending on where the Sun happened to be in its roughly 11-year activity cycle, swelling outward during periods of high solar activity and contracting inward during quieter stretches, similar to a lung expanding and contracting with breath. Voyager 1 crossed during a period of high solar activity in 2012. Voyager 2 crossed 6 years later, during a noticeably different point in that same cycle, and from a completely different direction. If that breathing bubble model held up, the 2 crossings should have happened at meaningfully different distances from the Sun. They didn't. Both spacecraft found the heliopause at almost exactly the same distance, roughly 11 billion miles out, despite crossing at different phases of the solar cycle and from opposite sides of the solar system entirely. "We don't understand why that is," said Stimatios Krimigas, a longtime instrument lead on the mission at the Johns Hopkins Applied Physics Laboratory, in a statement issued alongside the published findings. That's not a dramatized line inserted for effect. That's a career physicist, on the record, through NASA's own communications office, acknowledging that a reasonable, well-established prediction about the shape and behavior of our solar system's edge simply didn't hold up once it was actually tested against direct measurement twice from two different locations. The second surprise involved magnetism, and it built directly on something Voyager 1 had only hinted at years earlier without being able to confirm on its own. Before either spacecraft reached the heliopause, the standard expectation was that the magnetic field on either side of the boundary should differ sharply. Inside, the sun's own field, carried outward by the solar wind. Outside, a separate field generated by the broader structure of the galaxy itself. Two distinct systems, from two entirely different sources, expected to diverge clearly right at the crossing point. Voyager 1's single magnetometer reading beyond the boundary in 2012 suggested something different. The field just outside seemed to point in almost the same direction as the field inside. With only one data point, researchers couldn't be sure whether that reflected something genuinely real about the boundary, or was simply a coincidence tied to Voyager 1's specific location along an enormous irregular edge. Voyager 2 gave them a second, independent measurement years later, from a completely different position on the far side of the solar system. It showed the same alignment, two magnetic fields, from two entirely separate sources, sitting in close agreement with each other at the true edge of everything we call home. NASA's own science communications team described this directly, stating that the observation from Voyager 2 confirmed what had initially looked like a surprising, possibly coincidental result from its twin. That confirmation turned a curious anomaly into a genuine unresolved pattern, one that still doesn't have a fully settled theoretical explanation, and one that suggests our solar system isn't as magnetically sealed off from the rest of the galaxy as earlier models assumed. The third finding came specifically from where Voyager 2 happened to be positioned when it crossed, a vantage point its twin never had access to. Voyager 2 crossed closer to the flank of the heliosphere's overall bubble shape, rather than near the leading edge where Voyager 1 had crossed years earlier. From that different angle, one of Voyager 2's particle instruments picked up evidence, described in a statement from the Johns Hopkins Applied Physics Laboratory, that the heliosphere's outer boundary isn't a fully sealed barrier at all. A slow trickle of particles from inside our solar system was detected leaking out through the boundary into interstellar space, even as material from beyond pressed steadily inward from the other direction. Researchers involved in the analysis described the heliosphere, only half-jokingly, as behaving less like a sealed hull and more like a porous membrane, solid enough to shape and shield everything inside it, but never quite airtight, even at its supposed outer limit. Then there's the temperature reading, which sounds almost contradictory until you understand the underlying physics properly. Instruments on both spacecraft recorded plasma temperatures right at the heliopause boundary itself, somewhere between 30,000 and 50,000 Kelvin, comparable to conditions found near the surface of certain stars. Some science writers have taken to calling this region informally a wall of fire, an evocative description, but one that requires careful explanation rather than being taken at face value. There's no combustion happening out there, nothing burning in any conventional sense. Temperature, in physics, measures how fast individual particles are moving, not how much heat those particles can transfer to something sitting among them. Because the region is so extraordinarily sparse, with particles spread thin across billions of miles of space, there simply aren't enough of them colliding with anything to transfer meaningful heat. Voyager 2 passed directly through a measured plasma temperature that would vaporize almost anything on Earth, and its more than 4-decade-old electronics didn't register so much as a change in operating temperature, because there was almost nothing there to actually touch it. Put these findings together, and a pattern emerges that connects directly to a broader, still active debate in the field of heliophysics, one that exists specifically because of the dual perspective these two spacecraft together provide. For a long time, researchers generally assumed the heliosphere, our solar system's entire protective bubble, trailed behind the sun's motion through the galaxy the way a comet's tail trails behind its nucleus, stretched long in one direction. More recent modeling, built using data from both Voyager spacecraft alongside a separate NASA mission called IBEX, which studies the boundary remotely from Earth orbit by detecting particles that bounce back off it, has suggested the shape might actually be closer to a compact, croissant-like curve, deflated rather than drawn out into a long tail at all. That disagreement hasn't been fully settled, and every model proposed to explain the heliosphere's true shape has to be built around whatever these two direct crossings, taken 6 years and billions of miles apart, can actually support. It's a genuine reminder of just how much of our understanding of this entire region still rests on exactly two physical measurements gathered years apart from two different angles. None of these discoveries happened because engineers planned for them decades in advance. Nobody sitting in a design review in the mid-1970s decided that Voyager 2's plasma instrument should be built to outlast its twins by more than 3 decades specifically to help resolve a mystery that didn't even have a name yet. It happened because of ordinary hardware variants, the kind of small manufacturing and operational differences that inevitably separate two nominally identical machines built side by side on the same production line, launched only 16 days apart. And it happened because Voyager 2 simply happened to still be capable of direct measurement at the exact moment it mattered most, 6 years after its twin had already crossed the same kind of boundary blind. That kind of accidental redundancy is part of why both spacecraft continue to be operated with such deliberate, careful attention today, even as their power supplies keep fading year after year. Both Voyagers run on radioisotope thermoelectric generators, sealed units that convert the heat produced by decaying plutonium into electricity, and both lose a small, steady, unrecoverable amount of power every year, with no possibility of refueling or replacement once the source is exhausted. Voyager 2's plasma instrument, the one responsible for nearly every finding described here, was finally shut down in October of 2024, not because it broke, but because the mission team could no longer justify the power it required, given everything else on the aging spacecraft that still needed electricity to function. It had operated continuously for 47 years, more than 11 times longer than its original design life, and it went dark having already accomplished something no other instrument on either spacecraft ever managed to do. That shutdown is directly connected to what's happening with both spacecraft right now in 2026. Voyager 1 is currently the more power-constrained of the two, having already lost 7 of its original 10 instrument packages. Engineers at NASA's Jet Propulsion Laboratory are testing an experimental power restructuring procedure, nicknamed internally the Big Bang, designed to recover small amounts of electrical capacity currently being lost to inefficiency in each spacecraft's aging systems. Because any change to hardware this old carries genuine risk, the team chose to test the procedure first on Voyager 2, which currently has a slightly larger power margin, making a failed attempt there less costly to the overall mission. If those tests succeed, the same fix is expected to be attempted on Voyager 1 as well. In a quiet, almost fitting way, the roles between the two spacecraft have reversed from where the mission began. Voyager 2, once regarded as the slower secondary probe on the less glamorous trajectory, trailing behind its more famous twin for most of the mission's history, has become the test bed responsible for helping keep that same twin alive a little longer. Both spacecraft are expected to lose the last of their usable power sometime in the early 2030s, bringing an end to nearly 6 decades of continuous operation from two machines that were only ever designed to last 5 years. When that silence finally arrives, it won't come suddenly. It will be the last faint signal from an antenna that's been quietly reporting home since before most people alive today were born, arriving after a journey of many hours across a gap so wide that light itself, the fastest thing that exists, takes the better part of a day to cross it. Even after the transmission stop, neither spacecraft comes to rest. There's nothing out in interstellar space to slow them down, no atmosphere, no meaningful friction, nothing strong enough to meaningfully pull either one off its current course. Both are carrying identical copies of the Golden Record, the gold-plated copper disc holding greetings recorded in 55 human languages, the sounds of rain and ocean waves and human laughter, and 90 minutes of music selected to represent the breadth of human culture across our entire recorded history. It was assembled by a committee led by the astronomer Carl Sagan, built on the chance that someone, someday, somewhere far from here, finds one of these two aging machines drifting through the dark and wonders where it came from and who sent it. It's worth being direct and honest about what "can't explain" actually means here, since that precision matters more than any dramatic framing built around it. Nothing about these findings suggests anything supernatural, anything dangerous, or anything that breaks known physics. What they genuinely represent is a set of specific, well-documented observations, confirmed by NASA's own instruments and described plainly by NASA's own scientists, that simply don't yet fit within the models built to predict them beforehand. The heliopause, sitting at nearly the same distance despite very different solar conditions. Two separate magnetic fields aligning when theory said they shouldn't, a boundary that leaks material outward instead of sealing cleanly the way a simple diagram might suggest. These are exactly the kinds of gaps that drive real, ongoing scientific research, not evidence of anything mysterious in a supernatural sense, but genuine, openly acknowledged holes in our understanding of the region, separating our solar system from the rest of the galaxy, holes that only became visible once a working instrument was finally physically present to measure them directly. There's something worth sitting with in the fact that all of this came from a machine that predates the personal computer, running on hardware that would be considered primitive by nearly any modern standard, transmitting information across a gap so vast that light itself takes the better part of a day to cross it. Voyager 2 wasn't built with any of this in mind. Its original mission ended, on paper, in the late 1980s, decades before it ever reached the boundary where these specific findings were eventually made. And yet, because it kept working, because its plasma instrument survived long enough to still be functioning at the exact moment the spacecraft finally crossed into a region no instrument had ever measured directly before, it managed to hand scientists a set of genuine, still only partially resolved questions about the fundamental structure of the boundary protecting our entire solar system. That mystery is still unfolding right now as both spacecraft continue their outward journey, their remaining instruments slowly being switched off to conserve a power supply that cannot be replenished, their team at JPL working carefully through an experimental repair attempt that might buy a little more time to keep listening for whatever else this boundary still has left to reveal. Whether scientists finally settle the specific questions Voyager 2 raised about distance, about magnetism, about a boundary that isn't quite as sealed as anyone expected, before either spacecraft's last instrument goes dark for good, remains something nobody, not the engineers, not the physicists studying the data, not NASA itself, can currently promise an answer to. If you want to follow how this mystery continues to develop, and whether the ongoing repair attempts succeed in keeping either spacecraft's remaining instruments alive long enough to gather more answers, that story is still being actively written, right now, 11 billion miles from where you're sitting. Subscribe if you'd like to keep following where it goes.